So we're gonna do section 5.1. So that section is really just like a very short one on definitions of Hooke's law. And so I thought I'd bring you Rocky just to cheer you up. He's a good puppy. So yeah, he's gonna hang with us while we do this section. So let me just open it here. It's gonna be fairly quick and fairly simple. So basically, what it just does is it brings up Hooke's law, which it just provides to us kindly because we should know Hooke's law by now. So Hooke's law is just that the force is equal to a negative k, which is just a positive integer, times x. And what that then puts out is that at x equals 0, there will be a stable equilibrium of that force. And just to like quickly review what a stable equilibrium looks like is if I have a graph and it's in 3 sections. So this is gonna be my x-axis, and I'm gonna do a big middle one. That's gonna be my y. If I've got kind of like a graph like this, and this graph then has a flow, which means on this part of it, so on this section, draw sections like that, it's gonna be pointed towards the minimum. And in the middle section, the flow is going to be to the left. And then in the far right section, the flow will be to the right. And what this then means is that this equilibrium point right here, it'll be stable, which means that both sides kind of lead into it and then flood it. And the way to denote that graphically is just to have a wide open or like a completely closed circle. And then this one right here is going to be wide open, and that's going to mean it's unstable. So the graph is pulling it apart. So that's just a really quick, simple way to kind of remember that. And then the spring, since it wants to stay at that equilibrium, it'll have that stable equilibrium with Hooke's law. Okay, so then it sort of goes into a bit of what we can get more from Hooke's law. So the first thing it has us sort of recall is that the negative gradient of potential energy is equal to the force vector, as far as that's concerned. But what's really nice about this harmonic motion problem is that we're in 1D, so we don't really care that it's the gradient. We just know that we can take the derivative and get it. So what we're going to do to get the, or we can take the derivative of the potential energy and get the force. So since we have force, what we're going to do is the opposite of that. We're going to take the integral of the force, and we're going to end up with the potential energy. So we're just going to do that right here. So we're going to say that u x is going to be equal to the negative integral of f of x times x dx. And that's going to look like the negative integral of negative k x, which will just land us at 1/2 k x squared. And then, so that's kind of like the kicker of the whole section right here is just getting that. Everything else in the section just kind of like goes over a slight bit more used to it. Sorry, Rocky's used to knocking on doors, so he just likes to knock on them sometimes. Yeah, so we're just going to deal with that a bit more. So what we want to do is the book wants to go on to remind you that that also works for theta applications. So it can be 1/2 k theta squared, or yeah. And it wants to know that it has the exact same derivation. It's really just substitution at that point. But the book is going to take us a little bit further and kind of prove that Hooke's law and the potential that we get from that is really consistent. So what we're going to do is we're going to consider an arbitrary potential. So it's just going to be this function, and we're going to perform a Taylor series on it about the point of x equals 0. So to do that, we're going to have u of 0. We're going to have u prime of 0, and then we're going to have u double prime of 0 plus u triple prime of 0, and just like that's just going to go on for like ever. But what's interesting here is that this equals 0 at x equals 0, this equals 0, this equals 0, all these terms after it equals 0. So we're really just left with this right here. So whatever u of x equals, or I forgot to write some stuff down. Okay. I'm going to do that part again because I kind of messed up Taylor series for just a hot second there. Just going to write it out again. It's going to be a very similar principle. Just because I forgot a little small thing that's very important. So when we get to each derivative, it'll be x times u prime of 0. And then it'll be 1/2 of u double prime 0 times x squared. Yeah. And then plus all the others. I'm not going to write the third one out this time, but it follows that same pattern. So it'll be 1/6 times x to the 3, and then triple u prime 0. And only this one survives. So whatever u of x is equal to, it can be simulated around x of 0. It can be simulated by 1/2 x squared u double prime of 0. So what the book then does is it sort of says, all right, if that's true, we're just going to let u double prime of 0 equal k. And when we do that, we end up with u of x equals 1/2 k x squared. So that's just sort of another way of getting it. And that one just sort of proves that for small displacements, so somewhere around that equilibrium point, that Hooke's law is always valid. So as long as you don't like break your spring will work by Hooke's law. Or if you don't stretch it out to the point where the string becomes like less springy, like if you stretch out a slinky and then like the coils don't go back, it's that kind of vibe. So the only thing left in this chapter is there's this one example. So I'm going to sort of go through that with you, and it pulls from another section, so it's like weird. But basically what it says is I have a circle that I put a square on, and we're going to pretend I'm really good at drawing those. And then I draw a line from my circle into my square, and then I draw a line from that line into the center of my square, and I just start naming things. So this height here is going to be equal to h. So I'll close it off. This is going to be point C, the end point there. This is going to be point B. And then in the middle, we're going to call that 0, so the origin. And then in here I've moved theta degrees, and I have a radius of this little r right here, if it'll keep it. There we go. Okay. And then in the block, I have the line that I drew is going to be length b. So what it then does is it pulls out sort of its potential energy. And we're just going to kind of prove that we're going to prove this right here in this problem. So the potential energy of this entire system is going to look kind of like this. So U theta is going to be equal to mg. So we have that force of the gravity working on us there. And then what we're going to do is we're going to take sort of this line right here, and that'll be equal to 1 plus b. And we just want the part of it that goes up and down. So with this theta, so we're going to times that by the cosine of theta. All right. So the block is the one we're looking at. And it's got that mass m. And from there, actually I think the whole system might have mass m. Either way, the next part of the equation is going to be r times theta sine theta. And so this equation was sort of given to us by the book. And it was pulled out from a previous section. And what we're really just going to do is we're going to prove that we can get it to look like the 1/2 kx squared. And in order to do that, we make this approximation. So as long as theta is small, we can say that cosine of theta is going to be equal to 1 minus theta squared over 2. And then we're going to say that sine theta is going to be like approximated by theta. So it's okay that we use that small theta because, like we did in the Taylor expansion, we really want the small theta. So that's what matters to us. So from there, we're just sort of gonna rewrite this equation right here as the approximations. So we'll end up with u of theta is approximated by mg times, come on, r plus b 1 minus theta's minus theta squared over 2 plus r times theta squared. And then, oh, it didn't do the square. Okay, there we go. Oh, I should close this off. And then we're just sort of going to distribute from there. We're going to say that this is what we get. Well, we're going to get this just like algebraically redistributing. So then what's important to note is that right here, this is just some constant. So we can rewrite that as just, keep it consistent with the color, some random constant out there in the world that we don't really care about. I'm gonna be honest with you. And then we're going to carry down more of it. But what we're going to do is we are going to take this part and we're going to call that K. So there we have K. And we just end up with that theta squared left. And this is what we were looking to get anyway. So that's all of this chapter. That's it. It just sort of goes over Hooke's law and how to use it for potential energy. Rocky has left me, but that was this section.